So beam stresses offer some interesting challenges. They vary through the thickness of the beam. So if we look at a beam here, we have high tensile stresses at the top, larger compressive stresses at the middle, and it goes to zero. Compressive stresses at the bottom, and it goes to zero in the middle. And if we look at the transverse shear, it looks quite opposite, right? It goes up, zero at the top and bottom, it peaks in the middle. And so we have this variation through the depth of the beam. But we also have variation along the length of the beam that's important to consider. So if we look at the stresses values that we have, they're functions of moment and shear stress, and those tend to vary along the length of the beam. And so we need to understand that. It varies based on the type of loading and the end conditions. Is it a fixed end? Is it simply supported? Are the two most common assumptions, but we could also have other things in between. So we need to understand those variations in order to be able to solve beams. So looking at these different beams, the shear is zero in some places, the moments might be zero in others, and the distribution varies based on the particular beam loading conditions. So when we think about this, we start with if we know the deflection, we could take the derivative and get the slope, which we take the derivative, and using mechanics, we know that's m over ei. We get the shear, we keep going down to a loading diagram. Now, typically, what we know, though, is the load, and so we have to go the other direction and integrate successively. So we would start with the loading diagram and get to a shear diagram, and for a shear diagram to get the moment. Those two will allow us to calculate the stresses, but if we're worried about deflections, then we have to continue integrating to get the slope and finally the deflection. And this is typically the direction we have to go. And along the way, with each integration, we get integration constants, and we need to use things we know about the boundary conditions in order to solve those. Now, there are a lot of ways that you can come up with information and solve for these different relationships. I want to highlight three that we're going to focus on. One is a table of solutions. This is what the text refers to as superposition. In actuality, we use superposition in a variety of these methods, but here we take whole solutions and we add them together. And you could look these up, for example, in the appendix of the textbook. We could integrate piecewise. That's probably the technique they taught you in your mechanics and materials class. It could be a little cumbersome because of the discontinuities. We integrate and we have to do a series of integrations across the length of the beam and make sure that they're continuous, that the values are, we have to make sure that we match those as needed. Then we could go to the singularity functions, which makes a lot of this a little easier because we could write one equation for the whole value. And we're gonna do a little bit with that. We'll cover that in some separate videos and discussion. Numerical integration is great because it's so easy to set up. It's very quick to set up a numerical integration in Excel. Then you can plot and look at the different factors of the beams. And finally, finite element analysis, which is the most general and can handle the most complexity, and depending on your settings, linear, nonlinear analysis. But it takes more work to get ready. And so most of the time, we're going to benefit from being able to use these hand calculations. Now, one of the things we want to know, if we think about the shear moment, is where is the shear moment going to be most severe? Where might they, are there places where they both are high, or so that we can think about the failure conditions? So a tool for doing that is creating shear moment diagrams, which is a plot of the shear and moment respectively along the length of the beam. So if the length of the beam here is x, this becomes our x-axis, and we're going to plot shear moment on the vertical axis. So to look at this, what we could do is we could section off the beam, and we can use free body diagrams to solve for what those shear moments would be. So, for example, on the left side, we could solve for the shear or the moment value that we have here. And then we could also do that section in the middle and solve for values. And we could do this repeatedly, or we could use what we know from the integrations. As we connect those points together, then we could draw a shear moment diagram. Key thing to recognize here is that a positive shear, if we look right here, the positive shear is oriented downward as the standard convention. And then the moment, a positive moment, would be one that makes a sort of, think about a smiley face, right? So if it makes a smiley face, then the moment's positive. This way it's going to curve downward, so this would be a negative moment. We could continue those integrations, right? If we write the shear moment, we could find the boundary conditions by free body diagrams, and also embedded in that is some assumptions about the joint types as far as to know which reactions there are. And then we could integrate to find theta and y. And these look a little bit different with other kinds of beam types. So for example, with the simply supported, we know that the moment equals 0 at both ends. And so we get a different shape. But we could still integrate, and we get deflection values as we go. And those techniques we talked about allow you to do that. We'll get into more of that in chapter 4.